All right, guys, so let's go ahead and move on to section 8.2. Remember that last time we talked about section 8.1, which was essentially the textbook explaining why we need a improved logic, right? One that will provide more concise language and have more expressive power. So that way we can express ideas in a cleaner, more elegant way, I think is probably the biggest benefit here. And so we're going to dig into some of the syntax and semantics of the first order logic here. And you're going to see as we go through it, especially when you go through some of those prologue tutorials, that they start to align, right? Because prologue is programming language for logic, okay? And it borrows a ton from these ideas that we're talking about right now. It's based on the ideas that we're talking about right now. Okay, so let's continue on. Now, remember, models themselves, what they were being used for, whether it was propositional logic or now first order logic, is that they allow us to describe possible worlds, right? Through the assignment of truth values to different symbols that can help us to get an idea or to describe, what's possible, a particular scenario that's possible, right? So different sentences in a logic, what they allow us to do is they allow us to take the vocabulary of those sentences and link them to elements of a possible world. So we had different pieces of those sentences that were representing things in some world, in some space, okay, some possible world in some universe. So we had symbols that were representing things. Because of that link to some possible world, we were able to then determine, the truth of any of the sentences in the logic. So in propositional logic, we saw that. And so what happened with propositional logic is that we had propositional symbols that we could assign to truth values. Now, models in first order logic do some similar things, but they're a bit more interesting. Okay, so when you talk about the domain of a model, okay, the domain of a model in first order logic, what you have is a set of objects, right? A set of objects. And these objects are also known as domain elements. And for reasons, right, we'll just leave it at that, the domain must be non-empty. And for our purposes, we don't really need to go into it. But the text talks about it a little bit, which you can review if you want to. But let's see here. So we're going to take a look at, I'm going to show you a figure here in a second that lays out in graphic detail what a particular model could look like. But let's consider a few objects here. Say we have Richard the Lionheart, King of England from 1189 to 1199. Fine. We got his younger brother, evil King John. He ruled from 1199 to 1215. What about left legs? Right? It's a simple or a silly example from the text, but whatever. The left legs of Richard and John, right? And then there are crowns. There are crowns in the possible worlds, okay? So these things can all be objects in a model, and it's possible for them to be related in different ways. Now here's this representation of the model that I was talking about, figure 8.2. So here we've got the objects laid out. So we got Richard, got a constant symbol R representing Richard, got J for John. There's a crown in this model. There's their legs. There's a relationship where they're both brothers. We can also say that they're persons. We can say someone's a king. Okay, so there's 5 objects here. There's 2 binary relations, and there are these 3 unary relations. And there's a unary function. We're going to go through all of these different things. All right, so that relation in the figure here, that Richard and John are brothers, That's one example of a relation. So objects can be related in different ways, and you can say that a relation is basically tuples. Right? You get a set of tuples, and those tuples are going to be representing related objects. So John and Richard, brothers. So here's our set, okay? And we can say that Richard, this tuple right here, we can say that Richard is the brother of John, and it goes both ways. We can say that John is the brother of Richard. Okay, so if you want to ask a question about Richard, well, who's his brother? John. If you want to ask about John, well, who's his brother? Richard. Okay, fine. So this is an example of a relation where we talk about a set of tuples of related objects, right? So you have another type of relationship. You can say that a crown is on John's head. And so you can say, okay, well, here's a tuple. It's not a set now, just a tuple, right? And we're saying that the crown is on John, okay? Now, both of those are examples of binary relations because there's two items, okay? There's two items, kind of like if you have a binary operator and you got two operands. Okay, those are examples of binary relations. All right, so now you have also unary relations. So an example of that would be, well, person. Okay, so person would be true for John and for Richard because John's a person, Richard is a person. Another way of thinking about unary relations is that they're properties, right? So you could say that the person property is true for both Richard and John because they're people. Now, the unary relation, the property of king, is true for John only. You know, once Richard passed on, once she died or whatever, if John committed regicide or whatever, you know, king's only going to be true for one of these people. Okay, for John only, once Richard has passed on. Now, some relations can be better expressed as functions. And so these, when you talk about them as functions, think about, you know, a mathematical function rather than, you know, a subroutine or a function in like C++ or something like that. That maps, you know, one thing to another, a one-to-one mapping. So each person has one left leg. So that model, that figure that I showed you, it's going to include a unary left leg function, right? So you're going to have Richard, and that's going to map to Richard's left leg. You're going to have John, and that can map to John's left leg, right? So first order logic models require total functions, and the textbook goes into this in more detail than we need to, but basically a value must exist for every input tuple. It's a one-to-one relation. Okay, the logic models require total functions, basically one-to-one mapping, one-to-one relation. All right, so let's talk about symbols and interpretations. In first order logic, you've got three basic syntactic elements, right? So three different pieces. And these things are going to represent objects, relations, and functions, right? So constant symbols are for objects, predicate symbols, those things represent relations, and then function symbols represent functions. Now, in addition, we can talk about having an arity, right? An arity. So each predicate and function symbol is going to have an arity. And all that is just a term that refers to, you know, specifying how many arguments these things can have, right? So if you wrote your own C++ function that had 3 parameters, you could say that had an arity of 3. And as you go through the prologue stuff, it's another term that's going to start coming up. You talk about different functions in prologue, and they talk about what their arity is. And so you're going to see that term pop up quite a bit. Now, models in first order logic, they have to provide some information to define their truth, just like, or to determine what their truth is, just like you had in propositional logic. Propositional logic, you went through and you figured out the truth of a model by, you know, we talked about the truth table enumeration algorithm or doing proofs, whatever, right? So in first order logic, you need some information to figure out truth too, but it's going to be a little bit different. To determine truth in first order logic, you have to provide an interpretation. So what that means is that you are basically mapping, or you're specifying, the objects, the relations, the functions. You have to grab those things and you have to specify what's being referred to by them, right? So you'll have a constant, you'll have a relation, you'll have function symbols, and then you map those onto the objects, relations, and functions within the model. And it'll make sense or it won't. If it makes sense, basically, if it makes sense, then it's going to be true. The model will be true. If it doesn't, then it's not a valid interpretation. The model is not true. So here's one possible interpretation to give you an example of that. We've got this symbol Richard, and that's going to refer to Richard the Lionheart. We've got this symbol John. That's going to refer to evil King John. We've got this symbol brother. That's referring to the brotherhood relation. On head, right? That can refer to the on head relation. That's going to hold between the crown and King John. If John's the king, on head is going to be used to refer to having the crown on King John's head. So person, king, crown, these things are all referring to sets of objects that are people, that are kings, that are crowns. So they won't have their own specific name like the object Richard the Lionheart. Or they don't need them necessarily. Or John, right? John is the evil King John object. But we can have this more generic term, person, refers to just what people, right? Or king to kings, or crown to crowns, right? You wouldn't name a crown John the Crown, right? So some of the objects within a model, they don't have to have their own specific name. Now left leg, we could say in this interpretation that refers to the left leg function, providing that mapping. One input, one output, one person to one leg. Now, you can have a lot of different interpretations, just like when we enumerated different models with that truth table enumeration algorithm. You had different possible worlds. You can have many possible interpretations and therefore many possible worlds here in first order logic. So we've got 5 constant objects. So what does that mean? There could be 25 possible interpretations using those symbols Richard and John. Okay. Now, as I was saying just a second ago, not all the interpretations need to name everything, right? You're not going to name, like I said, for crown, you're not going to say, oh, well, that's Tom the Crown. But for the king, for his brother, it probably makes sense in an interpretation to give them a name, right? Richard and John. Right? So, first order logic models, there is a set of objects and an interpretation that maps symbols to those objects. So you've got objects to constant symbols, predicate symbols to relations, function symbols to functions. And so just like with propositional logic, entailment, validity, that's all going to be, that's all going to be defined based off of all of the possible models. All right, so figure 8.4 is showing you what a set of all the possible models could look like. Right? So we've got R and J, we've got these names, we've got these constant symbols. Right? And so in this first figure, this is an example of where, there's only one object in the domain. And so we gave it 2 separate names. Okay, fine, you can do that. In the second circle here, it's another domain, and there's still one object in there. We're calling that object by 2 different names. R for Richard, J for John. And the arrow here is representing a relation. So here we're saying, the object is related to itself. Right? That's one possible interpretation. Does it make sense? Potentially, maybe, maybe not. Depends on what you're trying to describe. Now in the third circle, 2 objects within that domain. one of those objects are both named, Richard and John, and then the other object is nameless, kind of like how the crown was nameless in the previous interpretation that I mentioned. Okay, here's another model where there's two objects. Now in that model, each one of those has their own separate name. Fine. Okay, two different constant symbols, two different objects. All right, and so forth. Right, and the next symbol or the next circle over here, another domain. We see that there's an interpretation here where we've got constant symbol R for Richard, being assigned to one object, J to the other, and then that arrow is representing a relation between the two of them. I mean, there's all kinds of different combinations. Just if you have those 5 objects with those 2 constant symbols, and that boils down to a possibility of having 25 different possible interpretations just for Richard and John. Okay, so there's one more thing I wanted to mention to you too. There is an interpretation that's sometimes referred to as the intended interpretation. So when I went through here and I talked about this possible interpretation of the king example, if this is the one that you intended, if this is the one that makes the most sense, well then you can say that that would be or could be your intended interpretation. Okay, so the textbook talks about that and refers to logicians talking about intended interpretations. All right, so next up, let's talk about terms. Let's talk about terms. A term is just a logical expression that refers to an object. So constant symbols, they're a term. Now, you don't always need constant symbols to name every object. That's what I was showing you a second ago when we were going through all those different possible models. And, for example, didn't need to name John's leg. We didn't have to have a constant symbol for John's left leg. Call it Tom. So you can have something that looks like this. So what is this? This is a function symbol followed by arguments. So you can read this as saying, oh, well, this is the left leg of John. So you have your one input, and what's the output? This knowledge or this understanding that you're talking about John's left leg. Now, we're not, as I was mentioned before, we're not talking about actual function like in code, C++, whatever. This is a syntactical element within first order logic. So this is a shorthand way of saying, well, that's John's left leg, without having to give John's left leg its own constant symbol. Saying here, we're not calling John's left leg Tim. This is a way for us to imply what we're talking about, not an actual function. So the semantics are pretty easy for a term, right, where you're using this function notation. So if you have something looks like this, all this is saying is you've got some function in your model, you can name it whatever you want, right? So we're saying f, and then you have a bunch of these arguments. And those arguments are going to refer to certain objects within the domain. So that overall term refers to some object that's a value of a function applied to objects in the domain. So left leg, function symbol. John refers to King John. So, as I was saying a second ago, left leg of John refers to John's left leg. So rather than writing out in plain English, the left leg belonging to King John the First, which is got 5 toes and 6, it's 6 feet long, and we refer to it as Tim. Just say left leg John, right? It's easily understood. Okay, so for reference, lifting this from the text, figure 8.3, here's the syntax of first order logic using B and F, and creating a sentence. Let's just stare at this for a second. You can pause the video. What's a term? Right, we're going to talk about quantifiers and universal quantification and existential quantification here before we're done. And you're going to see that we're going to be able to combine some of this new stuff with some of the old stuff, right? So creating more complex sentences using those logical connectives that we saw in propositional logic. All right, so we can make atomic sentences, and atomic sentences are going to state some facts. So these things are also known as atoms. And so the way you create these things is you use a predicate symbol, such as brother, and you can follow them by a list of terms. So when you look at this, what does this mean? What does this atom mean? This is a fact, and that is to say that we got a brothers, or we have some brothers, and you read it from the left to the right. So what you're saying is that Richard is a brother of John. Richard is the brother of John. So you're modifying, I guess you're just looking at the arguments here and you're saying, well, from left to right. Richard is the brother of John. This is not saying that John is the brother of Richard. It only goes in one direction, okay? Now, these things can be really, really complex. So take a look at this. We've got some nesting going on. So you can have, as I was saying, you can have, a list of terms in here, right? Or you can just have one. So let's take a look here. What we're saying is that the father of Richard and the mother of John, even though we didn't explicitly name the mother of John, we didn't say, well, John's mother's name, we didn't give a constant symbol there. We didn't say, John's mother's name is Emma, and we didn't say that Richard's father's name is Max, right? Here it's just, we have a term, okay? Just like when we were looking at, back up here, left leg and John, okay? So what we're saying is, all right, the father of Richard and the mother of John, they're married. So Richard's dad is married to John's mom. So here's a quote from the textbook. Sorry. An atomic sentence is true in a given model if the relation referred to by the predicate symbol holds among the objects referred to by the arguments. Okay, so this right here, this is going to be true if in fact Richard's father and John's mother are married. Okay, so we can make very complex sentences, as I was mentioning a second ago, by reusing those logical connectives from propositional language. So we can make a lot more complicated stuff by using that propositional calculus that we studied previously in Chapter 7. So in that interpretation of the model, that example interpretation, here are some true sentences. So let's read these, right? So what this is saying is that the left leg of Richard, John, right? Left leg of Richard, John. Now, brother would say, if this not wasn't here, this would be claiming that the left leg of Richard is the brother of John, right? But since this not is in front here, this is saying that the left leg of Richard is not John's brother, and that's true. Okay, now what this is saying, this next sentence is saying, is that Richard and John are brothers. Because you have to go both ways. You're saying Richard is the brother of John, and now you're also saying with the and that John is the brother of Richard. Okay, with this next sentence, you're saying that either Richard is king or John is king, and that's true under our interpretation. Okay, and now what you're saying here is that if King Richard, or if Richard is not the king, that implies that John is the king, right? So these things can get really, really expressive. They can get really, really complex. So let's talk about quantifiers, and quantifiers are going to be where it really pays off for us here. So quantifiers, what they allow us to do is talk about entire collections of objects. And so these things are going to allow us to write one sentence that refers to whole collections. So remember when we were talking about how nice it would have been if we could have said something like, hey, if a breeze has a square in it, or excuse me, if a square has a breeze in it, then there's a pit nearby, and just have that one sentence rather than a sentence for every single square. Quantifiers are going to help us do that. There's two types, universal and existential. The upside down A is the universal quantifier. The backwards E is the existential quantifier. And the universal quantifier is often read or interpreted as for all. Existential is often read as there exists such that. We're going to look at the universal quantifier first. So in first order logic, we could write a sentence, all kings are persons, as this right here. For all x, you can read this as for all x, if x is a king, then x is going to be a person. Right? For every single domain entity, for every single object, if it's a king, then it's going to be a person. Now x in that sentence is known as a variable. By convention, variables are lowercase. They're considered terms all by themselves. They can be passed to functions, such as left leg here. And if you have a term without variables, that thing is known as a ground term. Now if you take a look at the sentence for all xp, if p is representing any logical expression, this is saying that p is going to be true for every x, right? For every object x in an extended interpretation. Another way to put it is that for all xp is going to be true in some model if p is true in all of the possible extended interpretations constructed from an interpretation given in that model. And x is referring within that interpretation to some domain element. Okay, so sounds complex, really not. So let's go back and take a look at, consider our previous interpretation. Let's extend that thing out and say, all right, well, x refers to Richard the Lionheart, x refers to King John, x refers to Richard's left leg, x refers to John's left leg, the crown. Right? So if x is referring to each of those things, when we talk about this, then for all x, king of x implies person of x. Anything that is a king is also a person. This is going to be true in our model that we looked at originally back when we started this. If king of x implies person x is true under each of the above extended interpretations, right? Where x is Richard the Lionheart, or x is King John, or x is Richard's left leg. So that one universally quantified sentence, it's equivalent to all of this. Right? Rather than having to write out 5 different sentences, we can write this one sentence. And if we plug in each of these values, each of these objects for x, then we get these 5 sentences. Richard the Lionheart is a king, implies Richard the Lionheart is a person. King John is a king, implies King John is a person. Richard's left leg is a king, implies Richard's left leg is a person. So this one sentence represents all of this under the interpretation. Now, there's only one of these sentences that are actually correct. The second one, King John is the only king, so that's the one that's correct. And remember in our model, that figure that I showed you earlier, let me scroll back to it just to remind you. Right? Way back, right? So here we go. This right here, John was the only king, right? So the only sentence that was actually true under that extended interpretation was the one where we had King John as x. Right? Or excuse me, King Richard as x. Sorry. So King John is a king, which implies King John is a person. So the first part of the implication was true. Right? So that's what made that second sentence correct. Now, Richard the Lionheart is king? No, not in our model we looked at. Not in that interpretation. Richard's left leg? Nope, that's not king. John's left leg? Nope. Crown? Nope. Only King John was the king. So the second sentence is correct. Now, the other sentences, it's weird. They're true. based off of what implication means, they're true. The whole sentence is considered true. The implication, I should say, is considered true. They're not correct, but they're true. Right? Why? Because if you look at the truth table, P implies Q. The only time you have an implication that's false is if the premise is true, but the conclusion is false. Right? So if you look at where premises are false, okay, they're still true, no matter whether their conclusion is true or false. Okay, so you look at Richard the Lionheart is a king. Well, that was false, right? But the conclusion was true. Therefore, the entire implication was true. Richard's left leg is a king. Well, that was false, right? Now, Richard's left leg is a person. Well, that's false too, but false and false is still true. Okay, now that's really confusing. It looks really weird, but that's going to allow us to do some things. Okay, so basically what that allows us to do is create assertions or make an assertion for a conclusion for a rule just for objects where the premises are true. And we don't have to care about any of the other situations where the premises are false, because all we're trying to say is for all kings, for all objects that are kings, I should say, for all objects that are kings, they are a person, right? So logically you can disregard everything else because we're only interested in if it's a king or not, right? So if it's a king, if that's true, then we can follow up and say, all right, well, if that premise is true, then let's worry about the conclusion of that. For any other sentence where that premise is false, who cares? Because we're only interested in wondering or answering the question, is a king a person? All right, so here's a common mistake the textbook points out. Sometimes when people want to say, well, if it's a king, then it's a person, you might write a sentence that looks like this: for all x, king of x and person x. So what that's doing is it's making assertions that look kind of something like this: that Richard the Lionheart is a king and Richard the Lionheart is a person. King John is a king and King John is a person. Richard's left leg is a king and Richard's left leg is a person. That's not what we were originally trying to figure out. What we were trying to say, well, that's not what we were originally trying to say. What we're trying to say was, if you're a king, you're a person. It's different. Here it's saying, well, you're a king and a person. King John is a king and a person. Richard's left leg is a king and Richard's left leg is a person. Right? So it's kind of giving you two facts about this thing, right? About this object, rather than saying, if you're a king, then you're a person. It's different. All right, so let's talk about existential quantification. So this is different in that you're not talking about everything that could be in the universe. You're making a statement about one thing, and you're not giving it a name. You're not spelling it out. This one thing. You're not saying this. You're not giving it a name, right? So you're not saying, John, right? You're not saying Tim, right? You're just saying there is this thing in the universe that has this property. So if you wanted to say King John has a crown on his head, what you're saying is there exists a crown, right? There exists a crown, and that crown is on John's head. Right? We didn't specifically name the crown. We didn't say Tim the crown is on John's head. We didn't say Alpha the crown is on John's head. We're saying there is a crown in the universe, and it's on John's head. Or another way you can put it is King John has a crown on his head. So there exists this thing in the universe for an expression P, and that is true in a given model if P is true and at least one extended interpretation. So if at least one of the following is true, Richard the Lionheart is a crown and Richard the Lionheart is on John's head, or King John is a crown and King John is on John's head, or Richard's left leg is a crown and Richard's left leg is on John's head, or John's left leg is a crown and John's left leg is on John's head, or the crown is a crown and the crown is on John's head. So since that fifth assertion is true, that existentially quantified sentence is true in the model. There exists a crown and it's on John's head. So fill in for X, every one of those objects, at least one of them is true, so that sentence is true in that model. So from the examples we can see that implication goes very naturally with the universal quantifier, the AND connective. It's easy to see that it's pretty natural for it to be combined with the existential quantifier. And if you pair AND with the universal quantifier, you're making a really strong statement. You're saying everything in the model, for all the objects, both these things have to be true. As it turns out, implication with the existential quantifier, in contrast, makes for a pretty weak statement. So if you consider a sentence that looks like this, there exists something that if it's a crown, then it's going to be on John's head. So that's stating that at least one of these things is true. Richard the Lionheart, if Richard the Lionheart is a crown, then Richard the Lionheart is on John's head. King John is a crown, then King John is on John's head, and so on. Now remember, an implication is going to be true if its premise and conclusion is true, or if the premise is false. If the premise is false, it doesn't matter what the conclusion is, the whole thing's going to be true. So if Richard the Lionhearted is not a crown, and he's not, that first assertion will be true and the existential is going to be satisfied, right? So this first part right here, that the premise, Richard the Lionheart is a crown, well, false. Now, since that's false, according to the truth table, according to how implication works, this sentence, the whole thing evaluates to true. Therefore, this sentence, there exists an X such that if it's a crown, it's going to be on the head of John. That thing's true. So we're not even evaluating all the other sentences. The existential has been satisfied. Does that make any sense? No, but it is satisfied. So that's not really useful. Okay, that's not really useful. Using existential quantifiers with implications, not very helpful. Right? So pretty darn weak. All right, so you can combine quantifiers to make far more complex sentences. So in the simplest example, you got quantifiers that are the same type. If you wanted to say something like brothers or siblings, then you can say, well, for all x and for all y, if x is a brother of y, then that implies that x is a sibling of y, right? So anybody who's a brother of y, that means they're a sibling, right? Another example, you can have a symmetric relationship using a biconditional. And so you're saying for all x and for all y, x is a sibling of y if and only if y is a sibling of x, right? You can mix them, the existential and the universal quantifiers together. For example, if you wanted to say, well, everybody loves somebody, you know, one way you can interpret that is to say, well, for every person, there's someone that person loves. So if you look at this from the inside out, it might be easier to see that. So if you say, well, x loves y, now you add this existential quantifier on it, then you're saying, well, there is at least one y. And then if you put the universal quantifier on here, you're saying there's at least one y where everybody loves that y. Okay, and if you reverse that and you say there, you know, if you reverse those quantifiers, it has a different meaning. You're saying there is someone who is loved by everyone. So start from the kind of the inside out. And you say, well, x loves y. You can say, well, for all x, everybody every X loves some Y. There is someone who is loved by everyone. Okay, so putting parentheses around that might make it a little bit easier to see that. All right. Can be confusing. It can be confusing when you use the same variable for two different quantifiers or for two quantifiers. So you take a look at this sentence right here. Consider this thing, right? The rule is that the variable belongs to innermost quantifier that uses it. So right here, this quantifier is inside. It's in the innermost parentheses, right? So you've got for all X, that's modifying this entire thing, right? But you have an existentially qualified X, or quantified X, I should say, that's part of this piece right here. So the X belongs to the existential quantifier, right? So this X right here belongs to the existential quantifier. So what that's saying is that, you know, you have a sentence about Richard, and you're saying that he has a brother, right? So Richard is the brother of somebody, of some X, right? So that's what that X is referring to. It's referring to this. This X is not subject to the universal quantifier because, you know, it belongs to the quantifier that's the innermost quantifier, okay, in terms of the parentheses. Okay, so if you want to avoid confusion, like in any programming language, just use different variable names. So negation connects the two different types of quantifiers in maybe not such an obvious way. So take a look at the sentence right here, right? So what this is saying is that there's nobody who likes parsnips, right? So, you know, if you pull it apart, you know, the function here is saying, well, X likes parsnips, right? But then if we then negate it, we then say X doesn't like parsnips. So then if we say for all X, we're saying any possible X, anybody you can plug in here doesn't like parsnips. So this is saying nobody likes parsnips. Okay, all people don't like parsnips. Now that's equivalent to the second sentence here. Let's pull that apart. Start off with this part right here. You're saying there's an X that likes parsnips. But then if you say the existential quantifier, you're saying there exists at least one X that likes parsnips. Now if you put the not in front of that, you're saying there does not exist at least one person who likes parsnips. Okay, so to summarize, you know, it's like saying everybody doesn't like parsnips. That's what this first sentence is saying. Everybody, all X, all people not liking parsnips. That's the same thing as saying there is not someone who likes parsnips. And so this is saying there's not, that's what the not is. I can't get that, I can't get the highlight right, sorry. There's not someone who likes parsnips. It means the same thing. Nobody likes parsnips, or there is nobody who likes parsnips. Okay? So the negation basically makes them logically equivalent. Another example, everyone likes ice cream is the same as saying there is no one who doesn't like ice cream. So here, let's pull it apart. X likes ice cream. And here you're saying, well, all X's, everybody likes ice cream. And then down here, you're kind of using double negation, right? So you're saying nobody likes ice cream. And here you're saying it is not the case that there's someone who doesn't like ice cream. So X doesn't like ice cream. The existential quantifier X would say there is someone that does not like ice cream. But if you put a not in front of that, then you're saying, well, there is not someone who doesn't like ice cream, right? So those are logical equivalent too. You know, everyone likes ice cream is the same as saying there is no one who does not like ice cream, right? So hopefully you can kind of pull that apart and see that. It can be a little confusing, but it's all in how you phrase things and how you write the sentences, right? All people like ice cream is equivalent to saying there is not even one instance of a person who doesn't like ice cream. All right, so you can specify that two terms are going to refer to the same object using the equality symbol. So here you're saying that father of John is referring, you got the function here, and you're saying that this is referring to the same thing that this constant symbol is referring to, right? So you got two different things referring to the same object. How can you determine truth? Check both terms are referring to the same object. You can use negation to insist that two terms aren't the same object. So if you want to say there's two brothers for Richard, you can say, well, there exists some X and there exists some Y such that X is Richard's brother and Y is Richard's brother, but X equals Y? Nah, right? So all of these things have to be true in order for the and to be true. So we're saying Richard has two brothers. Now, if we leave out that they're not the same person, which is what we're considering here, right? We left out the not being the same, then that would be saying that Richard has just one brother. And there's a mistake on the slide here which I need to correct, but I should say here assign King John to both X and Y, right? So if I assign King John to both X and Y, then you're saying, well, there exists somebody, and so if somebody is King John, right, and you can, since you didn't say that they can't be the same, you could assign King John to Y also. So then this whole sentence would say, well, King John is the brother of Richard, and King John is the brother of Richard. Well, both those things are true. So then this whole thing would be true. And so you're saying, well, there's just one brother in that case, because it would make the entire thing true. Since we forgot to leave out this piece right here, or we left out this piece right here, we didn't require that they're not the same person. We just said that King John is Richard's brother twice. Okay, fine, true and true is true. All right, so come back next video. We're going to go through some examples of using first order logic in section 8.3. Hopefully at this point you're feeling somewhat comfortable with first order logic. You know, what did we talk about? We talked about the three different types of objects, you know, how you can name things, talked about relationships, talked about functions, which can help you to, you know, implicitly refer to objects within a particular model. You have to evaluate the truth based off of a particular interpretation, and we added, you know, the two different types of quantifiers, universal and existential, and those really give us the power to not have to repeat ourselves over and over and over and over and over again like we did in Wampus World.